Hello students. So today we are going to continue our discussion on MOSFETs, which we started in the 2 classes back. So in the last class, if you remember, we discussed about output characteristics of enhancement MOSFET, and we discussed that the different regions of this system that we have seen. We have also came across about different voltage values, how we should set those voltage values, triode region, saturation region and all. So I asked you to try to draw the transfer characteristics from that. I hope you have all done that. So here, just to highlight one particular thing, I just want to emphasize on one particular thing, that in the triode region, the slopes of all these curves are again going to be different, because increasing VGS actually puts more charge in the channel in the enhancement MOSFET. If you remember, the entire method procedure was based on the phenomena of inversion, and if you increase VGS, then more and more charge is going to be pushed inside the channel, allowing more drain current to flow. And thus, if you increase VGS, the slope of the curve is going to change continuously, and that should result into something like this, where you have all these curves with different slopes. Okay, so today we will just discuss the other side of the story, the depletion kind of MOSFET, and you will see slowly, gradually you will understand that what are the major differences, not only construction wise but also working wise, between enhancement type operation and depletion operation. So depletion MOSFET is basically a structure which is quite similar to JFET, because here you have this N channel. We are again talking about N channel devices, and you can extrapolate these to understand how P channel devices work. So here you have this N channel already existing between your source and the drain terminal. Otherwise, the entire structure is exactly same. You again have a P-type substrate, you have N-type or N+ type source and drain, and you have a gate exactly similarly separated by a metal terminal and an oxide layer, which is an insulator. So except for the existence of this N channel, which already connects the two source and the drain, there are no construction wise difference. That is the main difference that we have. So as here you already have a channel, so then even if we don't apply any voltage, we have VGS equal to 0. You as we have seen in case of JFETs, if you remember, we started with discussing about this case of VGS equal to 0 there also in case of JFETs, and here also for VGS equal to 0 you are going to have a current flowing in the circuit, right? Because if you attach a battery where positive side is attached to the drain, then the N channel will be filled up with the electrons which want to go in this direction because of the presence of this VDS battery. So in case of VGS equal to 0 also, you will have a current flowing in the circuit and corresponding to the charge flow through the channel. So here you can see that I have again short circuited the gate and the source terminal to make sure of the fact that VGS, the gate to source voltage, is 0. That is my control voltage. If you remember, throughout the field effect transistor, VGS is my control voltage, and that is still 0. So based on this, if I just try to draw the basic idea of how the circuit works, then here you can see that as I go on increasing VDS, the phenomena that happens is ID is must be increasing, because we have more and more attractive force for the electrons present in the N channel. But at the same time, we have this PN junctions here, right? So this is P-type, this is N-type, and we have a PN junction where the N-type side is connected to the positive side of the battery, and the P-type side through this substrate is connected, short-circuited with the source, and then it is connected to the negative side of the battery. So P-type side is again negative, having a reverse bias compared to the N-type side, right? So in this situation, we have a similar kind of scenario arising as JFET, because as you go on increasing VDS, this particular biasing that we have creates a depletion region which expands on both sides of the junction. So you have this range of depletion region which goes on increasing as you go on increasing VDS. So the current though increases as you increase VDS, the depletion region also grows inside the substrate as well as inside the N channel. So the obvious is that as you go on increasing VDS at a certain value of VDS, exactly like JFET, the depletion region will be enough to close down the channel inside the near the drain terminal, right? So similar phenomena that we've seen in JFET, similar thing happens here in case of VGS equal to 0 also, and you get a pinch off. So if I want to draw, let us just today draw the output characteristics at the same go as we are discussing the device, because by now you already know how these output characteristics are drawn. So here I have again the drain current, the output current in the y-axis, and the drain source voltage, that is VDS in volts, in the x-axis. And if I want to draw that how current changes, so we saw that the current should increase linearly up to a certain point, right? And then as soon as the depletion region grows and closes down the channel, it should turn, give a knee-like structure and then saturate. So this will be my graph for VGS equal to 0 volt. So now let us just think about a major striking difference that we have in case of these devices, which is different from whatever we discussed in JFET. So here one interesting part is that in case of JFET we saw that this current, this saturated current that we had here, IDSS, that was the maximum current that can flow in a JFET. That we have mentioned and emphasized several times, that IDSS, the current flowing through the device when VGS is equal to 0 volt, is the maximum current that can flow in this particular device, right? But in case of depletion MOSFET, if we just extrapolate this scenario, you will see that the same argument is not true here. So let us consider a scenario where I have VGS greater than 0. So let us consider the case 2 where we have VGS greater than 0. So we have attached a battery now where the gate to source voltage is positive and my battery is attached in this particular kind of way. Okay, so if I have a scenario like this, then what do I expect? As soon as I make my gate terminal more and more positive compared to the source, then the same thing that was going on in case of VGS equal to 0 will go on happening, because if the gate is more positive compared to the source, it is going to attract more and more electrons inside the channel, right? So the number of carriers inside the channel that are causing the drain current, then that number is going to increase, because this positive side of battery will attract more electrons from substrate, the p-type substrate, to the N channel, enhancing the number of electron in the channel and thus enhancing the current. So the same thing, like pinch off kind of a phenomena, will happen here as well, but here the current that is flowing into the channel is much more. Okay, so if you have VGS greater than 0, then the drain characteristics become something like this. So we go on increasing VGS a little bit, VGS equal to 0.5, 1, 1.5 on the positive side. What you have is more and more higher and higher saturating current, because this time they are attracting this voltage, the voltage that you have applied is attracting more carriers into the channel, enhancing the amount of carriers into the channel and enhancing the drain current thus. Okay, so if I now consider this scenario of VGS is equal to positive, I can actually get currents which are higher than IDSS. And that means that the main difference that we see here from JFET is that you can have currents, saturating currents even higher than IDSS. Okay, so VGS equal to 0 volt is not the ultimate limit of the maximum current flowing into the circuit. So that is one side of the story where we have figured out what is the difference between JFETs and depletion MOSFETs who are similar in working principle in quite a large number of parameters. Now let us look at the third side, the third story where we have VGS less than equal to 0. So we discussed VGS equal to 0. We have discussed VGS greater than 0. Now let us talk about VGS less than 0. So now you can see that I have connected a battery where the negative side is connected with gate. So VGS is made negative. So now your gate is at a more negative potential compared to your source. So in this situation, what happens is my gate is now negative. Thus, instead of attracting the electrons from the p-type substrate, it starts attracting the majority carriers. Those are the holes, right? So the holes of this p-type substrate will get attracted to this negative side of the battery, and because of this insulator, they will not be able to flow and they are going to get crowded inside the N channel. The N channel is filled up with electrons, right? So as you go on increasing VGS to some negative value, more and more holes will go on inside the N channel and they will start recombining with the electrons present there. So the number of electrons inside the N channel will start falling drastically, and slowly you will get it will reach a state where this N channel does not have any carrier near the drain terminal and the channel pinches off. So this is the scenario where you have VGS off, that is the voltage, that is the negative voltage that we have, where you have VGS off beyond which no current can flow through the device. So that is my cutoff voltage VGS off. Okay. So if I add this portion also in my graph, then what I get VGS equal to 0 graph sitting in between. On top we had this plus VGS graphs. Below this particular VGS equal to 0 graph, now we have these curves where VGS equal to -1 volt, -2 volt, -3 volt and so on. As you go on increasing this negative bias at gate, at a certain value it cuts off, where the number of holes are so many inside the channel that there are no more electrons left in the channel and there is no more current flowing. So VGS off is that limit where the current stops flowing. Here also in a similar fashion you can detect different regions like saturation, triode or ohmic region, cutoff region, etc. So this is the complete output characteristics graph. Let us have a more closer look at this graph. This is my IDSS. As you can see, this is my IDSS, which now is not the maximum current, and this device that we discussed can act, if you can just think about it, then it will be operating in both modes. One we call enhancement mode, another one we call depletion mode. So for positive values of VGS, the device acts in an enhancement mode where the current enhances and it attracts more and more electrons into the channel to increase the current. On the other hand, for VGS equal to negative voltages, it acts in a depletion mode and it squeezes down the channel gradually and finally choking the channel completely at VGS off. Okay, so this device, which is the depletion mode MOSFET, is sometimes also called depletion enhancement mode MOSFET or DE MOSFET because it can function in both depletion mode as well as in enhancement mode. So this is the basic drain characteristics, output characteristics of a depletion type MOSFET, which is very special because it combines all the features of enhancement MOSFET, JFET together and can function in several different modes. So let us just quickly discuss the transfer characteristics here, which is also going to be special. As you remember that in case of JFETs, we had a transfer characteristics where it started on the second quadrant at IDSS and dropped down to VGS off, where we reach the cutoff region, right? So a similar portion of the graph is still here, and this region is actually basically corresponds to the curves of depletion mode, which we have below the IDSS. So this portion, which functions exactly like JFET, is is basically characterized by this negative side graph in the transfer characteristic. On the other hand, for positive values of VGS, the current can increase further and further, and here the current enhances because more and more electrons are being attracted, and this portion which is in the positive first quadrant, positive side of the VGS axis, that is basically corresponding to the enhancement mode operation of my device. So this is more or less the entire discussion about depletion MOSFET. Read it out, try to understand whatever we have discussed. If you have any doubts, please let me know, and try to figure out some more aspects of whatever we have discussed so far. You can extrapolate that to understand how the curves will look like, the output characteristics will look like for p-channel enhancement type MOSFET or p-channel depletion type MOSFET. Okay, you can also extrapolate and draw the transfer characteristics for the same devices. So you can draw basically 4 devices, p-channel 2 types and n-channel 2 types, and again transfer and output characteristics, total 8 graphs of these different devices. Detect different quadrants where this curve should belong, and also consider the direction of current. So try this exercise at home. We have finished up our discussion on MOSFET. From the next class onward, we will start something new, discussing about some new devices.